So welcome again to a new lecture of solar photovoltaics course, Principles, Technologies and Materials. So we'll wind up today our discussion on PN junction and light with a emphasis on solar cell. So what we have been doing is we have done PN junction analysis and we have been talking of PN junction in the context of solar cell now, which is PN junction and light. So basically we have been looking at the device characteristics of PN junction in light, that is a solar cell. So essentially in this lecture we will also look at solar cell device parameters also. Okay. So let me just give you a brief recap. What we did in the last lecture was we looked at the so in the last lecture we looked at the the electron and hole currents under illumination. So the first is short circuit current, and of course the SCR current. All right, there are three components of the current. So first we looked at the short circuit current, which is basically a negative current, and what it meant was that under short circuit your V was equal to 0. So this was short circuit condition when the current you get is negative, and that is mainly because of increase in electron and hole population in you can say p type and n type semiconductors, right. So as a result you get the current which you do not get in forward current when you apply a bias. So essentially you get a negative current. What it means is that holes travel from electron n side to p side and electrons travel from p side to n side, and this happens because you have a you can say gradient in the or driving force due to splitting of Fermi levels. The electron Fermi level rises above the electron Fermi level in the n side. So basically you can say EFN for electrons in p side is greater than EFN in n side. Similarly, EFP for holes in n side is lower than EFP in p side. So you can say electron like to sink and hole like to float. So as a result, when there is a downhill gradient for a Fermi level for electrons will go from p to n side and holes will go from n to p side, and this happens because illumination causes massive increase in the carrier density, especially for minority carriers within p and n side. Okay, and this leads to the current in opposite direction, which is what and this current, as you apply bias, then ISC is countered by IV. Okay. So now when you plot this, you start getting a curve like this. So when you plot this, the I goes like this. So this is I, this is V. So this is at this 0 potential, this is V is equal to 0. So you are going from 0 to a parameter called as VOC. So at 0 bias, the current that we get is equal to ISC, which is called as short circuit current, and up to some point the bias induced current is not large enough. As a result, ISC stays nearly constant. Now this depends upon the type of solar cell that you have, material quality that you have, what kind of recombination you have. So for a perfect solar cell which does not have high level of recombination, which does not have high level of SCR current or other kind of currents, the ISC stays flat up to quite a bit of voltage, and before it suddenly starts increasing. So, within dark, for a dark solar cell, you should obtain characteristics like these, and this shifts to fourth quadrant when you apply when the solar cell is under illumination. So, this would be under dark and this is under illumination. And we also looked at the operation under two assumptions. One was long base diode and another was short base diode. So, which basically modifies the equations because in the long base diode, when the diode is very long, then you can say that Xn and Xp are much larger than Ln and Lp and Ln, right. As a result, surface recombination basically happens, and so everything will get recombined. So, as a result, you do not consider Sn and Sp because they would have anyway happened. In case of short base diode, you say that your Ln and Lp are larger than Xn and Xp and Xn. So, this region this is when the diffusion lengths are longer, then Sn and Sp are relevant because you will have surface recombination, and here Sn and Sp are not relevant. So, we made these two approximations, and when you make these two approximations, your diode equations change a little bit. However, when you whatever the case is, if you plot the IV characteristics of the solar cell, IV characteristics look like this. So, IV characteristics show a diode like behavior in the dark, and this curve shifts to fourth quadrant and giving you negative current at 0 bias, which is called as short circuit current, and this short circuit current starts reducing slowly and gradually, and it becomes 0 until you reach a voltage called as VOC, which is called as open circuit voltage. Essentially what happens is at this point is, if you now look at the total current, J total was equal to J bias, which is positive, and you can say if I, and this was J illumination, right. J illumination is negative, this is positive. At this point, these two components outweigh each other completely, right. And we also looked at the effect of various parameters on the quantum efficiency. We looked at the quantum efficiency shows a behavior like this. So, perfect quantum efficiency would be something like that. Okay. So, this is quantum efficiency as a function of wavelength. So, whenever the quantum efficiency reduces on lower wavelength side, which means your top of the solar cell is playing an important role, or if you have, so this would be the top part contribution, and if your quantum efficiency is decreasing on the higher wavelength side, then you know that you have decrease. This is mainly from the bottom part of the solar cell, and if you have a decrease in the middle, it comes from the somewhere in the middle you have recombination taking place or some other effects taking place. So, this will be helpful for you to look at your data yourself when you work on, if you work on solar cells, and analyze this in this context, that which of the layers may be playing important role in, especially from the important from the context of bilayer junctions like PN junctions, wherever you have silicon kind of solar cells. So, now what we will do is that we will now move on to, so these are the device characteristics that you get for solar cell under illumination. As I said, the current at 0 bias is called as the short circuit current, and the current and the voltage at which the current becomes equal to 0 is the open circuit voltage, and this is in, remember, this is in fourth quadrant. So, even though in literature there are some papers which which plots this in the first quadrant, you will see that there are enough books and literature which plot IV of solar cell like this. Technically speaking, this is not correct, but it is plotted for the sake of convenience, just to show that how much current you get from the solar cell, and this is the open circuit voltage. Technically speaking, this is a correct plot, this is not. okay, from the sign perspective. So, in the dark, a solar cell is going to behave in this fashion. You will have 0 dark current, and then you will have increase in the current at higher biases, and this curve shifts to 4th quadrant as you apply light, as you put it in light. So, under illumination you generate current from the solar cell, which is negative current, and this current gets outweighed. So, as I said earlier, the competition is between ISC and IV. One is negative and another is positive, and these two outweigh each other at this point. So, if you have more recombination mechanisms, this curve will start looking like this. So, in fact, IV will start dominating right from the early stages. So, for a perfect solar cell, the plot is like a rectangle, whereas for an imperfect solar cell with lot of recombination mechanism, defects, traps, etc., you will see this I starts rising as you increase the voltage in the early stages of the plot itself. So, this is, you can say, a bad solar cell device, and this is a good device or better device. Okay. The idea is to get as rectangular curve as possible. So, these are the two important parameters, ISC short circuit current, VOC the open circuit voltage. A lot of times we write this in JSC, which is short circuit current density, and this is nothing but ISC divided by area of the device. Okay. So, now we look at the effect of irradiation on this IV curve. So, effect of irradiation. So, this IV curve, which is, so if it is, let us say, for a solar intensity I1, okay, if this is the IV curve you obtain, if you look at the equation, since the current is directly proportional to the intensity, if you increase the intensity, the curve should shift down. So, and you can keep going in this direction. Ideally speaking, this is how it should behave. So, this will be upon increasing intensity of radiation. So, as we said earlier, we defined this in 1 sun, right. 1 sun is equal to AM, basically 1.5 G, okay, which is equivalent to 100 milliwatt per centimeter square. So, if let us say this was at 1 sun, then 2 sun should lead to, so this would be 1.5 sun, nearly 1.5 times increase, and this would be nearly 2 sun, theoretically speaking, provided there is no change in the VOC and there are other things which are not changing. Okay. So, generally it should show, ideally speaking, it should show double the increase in the current. VOC will not change because VOC, the voltage that you obtain is well, there will be some change because VOC is a function of current, but there is not a huge change that is seen in VOC. Similarly, if you as you change the temperature, the temperature change also. So, this is, let us say, and temperature. Okay. So, as you change the temperature change leads to, so this is increasing intensity. If I make a plot for this, for example, this is for the first temperature T1, and if you go it for high temperature, the high temperature leads to more emission, but also it reduces the VOC. So, as a result, high temperature will result in reduction in the VOC, generally like this. So, this would be, you can say, direction of increase in temperature. So, this is how IV will change as a function of temperature for a given, because you will be able to thermally excite a little bit more carriers as you increase the temperatures. So, some current will see some increase in the current, but it also leads to change in the voltage, as we will see later on. in the expression. This is what we discussed. So, a typical PN junction device is you have let us say in this case the emitter, then you have, or let us not talk in terms of emitter and base, that we will talk when we learn about the silicon solar cell. So, we will just restrict ourselves to, so let us say this is a N junction, this is a P type junction, then you will have a front contact here, and on top you will have a anti-reflection coating. So, this would be anti-reflection coating, which will, so it looks dark, but it should be transparent, all right. So, it should be transparent anti-reflection coating. On top you have metal contacts. Metal contact should be conducting enough, and they should have ohmic contact with the semiconductor. So, you should have ohmic contact, and then on the back also you have a contact. This is the back contact, which again should make a ohmic contact, so that charge carriers are extracted efficiently. And then as light shines on it, so as you have sun shines on it, the radiation falls over it, you create electron hole pairs in the semiconductor. So, the photon h nu will give rise to an electron and a hole pair, right, which is called as exciton. This exciton dissociates, and so this guy will travel to this side, this guy will travel to this side, and you will have and this is connected to a, let us say, external load. Some RL. Okay. This is what the typical solar cell geometry is. Of course, in case of, so this is followed pretty much in case of silicon, in case of thin film semiconductor devices such as cadmium telluride, CIGS, etc., but the geometry is different in case of solar cells which are, for example, organic or perovskites. In this case, although you have bilayer solar cells also, but the typical architecture is where P and N devices are mixed together with each other at microscopic scale, and in between the contacts there are also carrier selective coatings which preferentially allow certain type of carriers to go to, so holes will go preferentially to anode and electrons will go preferentially to cathode. So, this is a typical device architecture that we see for a solar cell. So, there is a, now solar cell may appear to you something like, what is the, so you have a solar cell, on the other hand you may have a battery. Okay. Solar cell is generally, it gives you characteristics which are like this. So, in case of solar cell, if you plot current as a function of voltage, so without bothering too much about the sign, you have something like this kind of behavior, all right. Okay. In case of battery, and this will change as you increase the intensity of light. So, intensity of light will move this to shift to right, your current will keep increasing, right. So, if you increase IS, your current will increase for a solar cell, whereas for a battery, battery gives you a EMF. If you plot V versus I for a battery, the battery IV curve is something like this, and there is no, of course, change with light. Of course, it may change with the temperature. So, it will give you a EMF which is corresponding to certain voltage, and then of course, it gives you certain current at voltage, and there is no change in the curve with light. Okay. So, in because we use both batteries and solar cells, battery is also a power generator, solar cell is also power generator, but there are fundamental differences between the way to operate. Battery is based on, basically you can say it's based on galvanic reactions, whereas this is conversion of light energy into electricity. Okay. So, this uses the things like electrolyte. So, of course, you have anode and cathode, but anode you have electrolyte and then you have a cathode. In this case, of course, you have anode, you have cathode, but in between we have a PN junction. These are the differences between the battery and a solar cell. So, in the context of solar cell, there is something you need to remember, that the device characteristics, if we looked at this plot earlier, the point in the IV curve, there is a point in the IV curve at which you get maximum power point, and this corresponds to the rectangle of maximum area that could be drawn within this IV curve. So, the rectangle that can be drawn is drawn by this blue line, the brown lines. So, the current and voltage corresponding to those is called as Vm and Im, and this point in this case is called as maximum power point. So, you can, now this of course can be determined mathematically wherever. So, basically you want to maximize the power. So, of course, if your IV curve is like this, the rectangle is also same as the IV curve. However, if your IV curve appears to be, let us say, like this, let me make another plot. So, if your IV curve is like this, okay, then the maximum power that you can extract will be somewhere here. So, this point is maximum power point, and the voltage and current corresponding to this point are called as Vm and Im. They are lower than Isc and JSC. So, basically you can see that if you just VOC and ISC. So, if you multiply ISC and VOC, this is the theoretical amount of power that you should be able to generate from a solar cell, but this is limited by the fact that you have device recombination mechanisms and so on and so forth, which we will see later on. Because of the decrease in the current as a function of voltage because of recombination and other issues, the maximum power that can be extracted from a solar cell is much smaller than what you can. So, this is where the shape of IV curve is extremely important. We should try to have, our aim as a materials and device engineer is to maximize this power that can be extracted, which means to have a IV curve which is as rectangular as possible. So, this, the current that we extract from a solar cell is depicted as JSC is equal to basically Q integral over all the energies, ISE, which is the incident spectral photon flux density, eta E is the quantum efficiency. Quantum efficiency will come from your current expressions basically. So, if your quantum efficiency is 1, then basically all the photons that you are able to capture will be converted to the current. However, quantum efficiency is not equal to 1 in most cases, it is always lower than 1 because of losses inside the semiconductor. As a result, if you capture 100 photons, if 90 are converted, then you get 90% quantum efficiency. So, this is basically the short circuit current, essentially theoretically speaking. And the dark current, as we have seen earlier, dark current J dark is equal to J naught into exponential of QVA by KT minus 1, and these two, so this current which is the dark current is basically is a positive in nature. So, this current is negative in nature and this current is positive in nature at positive biases, and these two basically compete against each other to give you a IV curve that we obtain for a solar cell. So, for a solar cell, J net basically is equal to JSC minus J dark. Okay. So, it is a balance between these two is what you get in a solar cell. So, JSC is at 0 bias, right, and as you apply the bias, this component starts increasing as bias is applied. Of course, you have to take care of signs. So, this is you can say this would be minus and this would be plus in the real context. So, this is the negative current and this is the positive current. So, these two outweigh each other, but if you just take the mod of 2, this is the current that you will obtain. Okay. So, when J net is equal to 0, I can balance out. When J net is equal to 0, then I can write VOC is equal to, so if you see the expression for J dark was equal to J naught into exponential of QVA by KT minus 1. So, I am saying that J net is equal to JSC minus J dark, assuming, so I am just taking the mod of both of them, just I am also taking JSC as a positive current. Okay. So, when J net is equal to 0, then in that case JSC is equal to J dark, and that is when V is equal to VOC, right. So, VOC can be obtained as, so if you now make it equal to JSC at VOC, okay, at V is equal to VOC, then I can obtain, I can replace VA with VOC. Okay. So, VOC will become KT by Q into ln of JSC by J naught plus 1. So, you can see from this factor, as the temperature increases, so as the temperature increases you will have some increase in VOC, but VOC is quite critically dependent upon the dark current and the short circuit current. It is a function of both dark current as well as short circuit current. So, if you have defects in the semiconductor, if you have recombination in the semiconductor, if you have anything which leads to higher recombination current or dark current, in that case your VOC will go down, and if you are able to increase the short circuit current, your VOC will slightly go up. Of course, it is a log, it varies as logarithmic function. So, the increase is not as much as you would see in case of current, but still there is an impact in certain terms on the open circuit voltage. So, based on the shape of this curve, we get another factor which is called as fill factor. Fill factor is the maximum power that can be drawn, maximum energy that can be extracted out of a solar cell, practically speaking, with respect to the maximum possible that you can extract. So, this is Vm into Jm divided by VOC divided by JSC. Okay. This is called as fill factor. It is a very important parameter in the context of solar cells. And last but not the least, we will just we will look at the power conversion efficiency. So, this power conversion efficiency is eta, which is Jm Vm divided by P incident. So, amount of maximum power that you can, so maximum power that you can extract or maximum energy that you can extract from a solar cell divided by what is the incident energy, okay, or incident power. Power extracted divided by power incident will give you the power conversion efficiency, which is nothing but JSC into VOC into fill factor divided by PS, which is the incident power. So, these are the solar cell device parameters that we have learnt in this class, and we will further discuss them in the next class before we go on to discussing the technologies. Okay. So, we will stop here today.